Okay, so we're going to just quickly review polar covalent bonds, polar molecules, but the focus of this is to go a little bit more in depth about the intermolecular forces that we had looked at the end of the last lesson. So just to recap, polar covalent bonds is when you don't really have an ionic bond, where they give and take electrons, and you don't have a non-polar covalent bond where you have an equal sharing of electrons, but rather you have an unequal sharing, or electrons that are not being equally shared between two nonmetals. That's considered to be a polar covalent bond. So why does this exist? It's because you have differences in the level of attraction between the two elements. So the electrons are attracted more to one side than the other. So then if you have a polar molecule, so here's a little guy, so this should actually have electrons here. You have now a difference in electronegativity. So hydrogen is 2.2, fluorine is 3.98. So you can see here that the dipole is pointing towards fluorine because it has the higher attraction for those electrons. Or you can have that delta symbol for slightly negative or slightly positive ends. So what happens here now, we have a new term called intermolecular forces. So remember to think of we're thinking about how molecules are able to interact with each other. So we're looking at forces of attraction between molecules and other molecules. There are 3 types. And actually, the way that this is listed is in order of decreasing strength. So hydrogen bonding has the strongest attraction between molecules. Dipole is in the middle. London dispersion is the weakest attraction, okay, of all 3 things. So what we're going to do is we're going to talk about what each one of these are and essentially what to look for. How do you know what molecules have, what attractive forces they possess? So I've already mentioned the strength. Actually, we've already gone through this. So let's talk about the strongest bonds first, or I should say forces. It's called hydrogen bonding, but actually all these things we're talking about, they're forces of attraction. So how you know that hydrogen bonding forces exist is you have to have hydrogen bonded to an electronegative element. So there's 3 of them that it can be. So hydrogen bonded to nitrogen or fluorine or oxygen. If you have any of these bonds in your molecule, that tells you that you have hydrogen bonding. Okay, so for example, here are molecules of DNA. It has nitrogen and hydrogen bonds. See how there's NH groups? So NH, as long as if you have NH in your structure, you have hydrogen bonding, but it could be any of these. So actually, if you think about it, water, right, which is H2O, it's hydrogen bonded to oxygens, it also has hydrogen bonding. And here's our water. So what happens here, and the lone pairs are not drawn in, but so the dipoles, I'll explain kind of what's causing this attraction. So what ends up happening is the slightly negative end of one molecule is attracted to the slightly positive end of the nearby molecule. So every slight negative end is attracted to the positive end of the next molecule. So see how this is one water molecule and this is another water molecule. It's attracted because opposites attract. So for example, we could have another water molecule here, and this negative oxygen would be attracted to this slightly positive hydrogen. These dashed lines are just showing you like, oh, this is where the attraction is, right? Like, this is where they're feeling the attraction. So positive ends are attracted to negative ends. Now, what makes them so special is because the OH, NH, and FH dipoles are very strong differences in electronegativity. So meaning the positive and negative is felt much stronger than in other dipoles. They are dipoles, but they're kind of a special category of dipoles. So dipole-dipole attraction is pretty much the exact same idea as what we just talked about, except instead of being OH, NH, and FH, it's any other dipole. So in order to have this type of attraction, it must be a polar molecule. Okay, you need to have dipoles there. And same thing with hydrogen bonding. Of course, it has to be polar, but it has to have one of these bonds. That's like the criteria to look for. So dipole-dipole happens in every single polar molecule. So what happens? There's attraction between the opposite charged regions of the neighboring molecules. The slightly negative end of one molecule is attracted to the slightly positive end of a nearby molecule. It's almost they're like little mini magnets. Okay? And lastly, this is the weakest interaction. This is called London dispersion forces. Oh, I guess I should show you the short forms I always use. So for hydrogen bonding, I like using the short form H bond. Okay, you're welcome to use these if you'd like. I use short forms for like everything. H bond. For dipole-dipole, I use dip squared. So it's like dipole is short form to dip, and then dip squared is like dipole-dipole. And then for London dispersion forces, I use L. Ooh, this is moving around. I use LDF. So I just use LDF. So, so when you're looking at this type of force, London dispersion forces happen in all molecules. It doesn't matter if it's polar or non-polar. London dispersion forces happen in every single molecule type. And I'll explain, it'll make sense once you understand what it is. So, essentially what this is discussing is that protons and electrons have opposite charges, right? So we know protons are positive and electrons are negative, right? So opposites attract. So what this is talking about is that basically when you have two molecules, right? So let's say I have like two little hydrogen molecules here. The protons inside the atom nuclei of one molecule will attract the electrons in the atom of the nearby molecule. So basically, protons and electrons will attract each other from nearby neighboring molecules. So every single molecule has this, because every single molecule has protons and electrons. So if you have a molecule, it does not matter if it's polar or non-polar, you're always going to have LDF as an intermolecular force. Okay? So what can cause a difference in this type of force is the size of the molecule. Okay? So the more protons and electrons that a molecule has, the stronger the LDF will be. So think of it, if I have a little molecule attracting, right, here I have really small, so it's only like 2 protons and 2 electrons attracting. But if I have a very big molecule, let's say these are all hydrogens, right? So let's say I have a very big molecule next door to another big molecule. Like imagine I have the same thing on this side. Even though these are non-polar, what's going to happen is the number of protons here and electrons here are more than comparing these two molecules. So the more protons and electrons molecules have, the stronger the LDF is. So remember, these are all forces of attraction. So what does that mean? That means these larger carbon-hydrogen structures have a stronger attraction for each other in comparison to these hydrogen structures. So what does that matter for us? Well, if you remember going way back to grade 9, when you're looking at particles, so little particle pictures, let's say I have a liquid versus a gas, right? So what determines the state of matter is the space between particles. So the reason why you have gases at room temperature is because the attraction between particles is very weak. Liquids have stronger attraction comparison to gases, and then of course solids are very compact. Their attraction between particles is very high. The reason why you have these different states of matter is because you have different attraction levels between atoms. So now you're learning what those attractions are. The attractions are either London dispersion, dipole-dipole, or hydrogen bonding. So the stronger the attraction, right? The stronger the attraction, the more likely a material is to be at room temperature a solid. If it's a very weak attraction, you're going to end up having a gas. Like, that's one property of matter. Intermolecular forces have a direct relationship with properties, right? Same thing with like melting point and boiling point. If you have a very strong attraction between particles and I want to melt my solid, it's going to take a lot of energy to break that solid down into a liquid. It's because you're trying to pull apart the particles to make more space between them. So that's going from basically solid to liquid is our melting point. Okay, going from liquid to gas is our boiling point. So again, this is making space between particles. So this is talking about what temperature do we need to increase this by to make the space between particles more. The higher the boiling point is, the more energy it will take to do that because there's more of an attraction between particles. So things like state of matter, melting point, boiling point, viscosity, all the different types of properties of matter that you learn about in grade 9, even in elementary school, they all relate to attraction between particles. So, going back to this, if you have larger molecules that have many dispersion forces, look at this. Large particles have high boiling points. Why? Because the LDF is stronger, right? There's more of an attraction between particles. Check this out. Small nonpolar molecules have weak dispersion forces and exist almost exclusively as gases. So things that have weak attraction are gases. If they have a strong attraction, they have high boiling points. Wouldn't you guess it? Wouldn't you know it? Right? It's because of the attraction between particles. So I'm going to pause the video because I really want to spend time talking about this graph here. We'll see you in the next part.